Students, welcome back to part C of the video. And in part C, we just started our lab, and we're doing it the barbaric way first, and then we're going to do the semi-barbaric way, and then we'll do it the right way using union root. All right, so here, as you recall, I set up my equation so that I have 141. I want 141 to basically equal, because remember, where is this coming from? This is coming from our slide right here. Again, I'm going to go all the way back to the top, right? I'm basically setting up this equation right here, and that's basically what I did in my code. I set up this equation. I want to change that compound return part, that 10%, so that my final result becomes 65,000. So that's basically, go down back here, oh, overshot it. So that's basically what I'm doing here in my code. Oh, actually, let me put this comment in here. I'll post this for you guys also. Barbaric way. All right, barbaric way. So here, this equals $56,156.10. We already know this. So how do I change R so I get 65,000? So let me do the for loop way, the barbaric way. All right. Now what I'm going to do here is I'm going to use a range of values for R in some sort of vector of values, right? We'll do that in a second. All right, and get these results. So first things first, I want to iterate through all these particular values in R. So I know I want to start with the 10%, at 10%, and I want to go up. I don't know how high, but I need to go up. So I need a range of values. So I'll create a range of values called, let's do A. How's that sound? And I'm going to use the sequence function to do this. So we'll start at 0.1 and we'll go all the way up to, I don't know, 50%, 0.5, and we'll step in terms of 1%, so 0.01. Okay, so if I run this line right here, A, down here you can see that A is going to be all these results, 10, 11, 12, 13, 14, 15, going all the way to 50%, right? And you can make it have more minutia if you wanted to. You can have less. I just chose the 1% increments. All right. So now I'm going to have R iterate through A and get these different results. Now, as these results happen, I would like to store these results, right? As it goes through R, I would like to store these results, because when I run this now, I'll run this for loop, right? It's calculating. Notice there's no output. There's no output because within the for loop, it's crunching the values, but it's not outputting it. To remedy this, I could use the print, right? I could use the print command if I wanted to, or I can store the values. So let's say hypothetically I store the value in a variable called res for result, right? Done. So let's say I run this. Okay, I got no output, but it's in res. I type in res down here, and I get $134,000. I ran this loop 41 times because A is of length 41, and I only got one value. Yes, because what happens is every iteration of the loop, res keeps getting overwritten. Res keeps getting overwritten. Keeps getting overwritten. To remedy this, I need to store the values of each iteration in res. I need to make res into a vector of length of 41 values rather than just keeping one value. How do I do this? That's right. I need to do the open bracket, close bracket system and store each value in the vector incrementally. So now I'm going to do, let's change this up. I need a way to basically change this value for every value in R. How do I do this? Well, I mean, I kind of hinted to that earlier on when we were doing for loops. We'll use a counter. So counter will equal 1. And so for the first loop, the first value of res will be whatever the first value of R will generate. And just to make sure we don't mess up, we want to increment CNT so that for loop 2, it'll be res will be overwritten in position 2, position 3, I'm sorry, +1, position 4, position 5, etc., etc., etc. So now I'll rerun this. Notice there's no output, but now when I type in res down here, ta-da! I now have a bunch of results. So excellent, I have my results right here. Notice we start off with the first value being $56,156.10. Why? Because let me make it slightly bigger so you can see it. So that's my results, and these are the R's that, oops, and these are the R's that generated it. These R's right here, so this is the A vector, R iterated through these values. So basically what happened is 10% generated this total amount after 4 years. Remember, 11,000 invested each year at a same compound rate, same return year over year. So 10% for 4 years generated that. 11% 4 years generated that. 12% 4 years generated that, and so on, so on, and so on. So we want to hone in on the output that gives us around 65,000. So when I go through these numbers, I see that 65,000 falls somewhere in between these two numbers, right? And so it looks like it falls within, which numbers are they? Well, using the aesthetics counts here on the side, I'll know. This row starts off with the 6th value. So this will be the 7th and the 8th value. Excellent. So 65,000 falls within the 7th and 8th value, right? The 7th and 8th value. Well, which return gave me, which compound return gave me these values? This is the 7th and 8th value. It's fair to say that it's the 7th and 8th value in A, compound return value in A, that gave me those results. So which values are they? I'm going to do a little slicing now. A 7 colon 8. Show me the values for the 7th value and 8th value for A, and it comes out to 16 and 17%. So my student, my fictional hypothetical student, looks like that they generated a compound return that falls somewhere between 16 to 17%. All right? And I got my answer. That's the barbaric way, the for loop. All right, now let me do this again. Let me run this back. And this time, let me do it the semi-barbaric way. And now we're just going to use a little bit of vector mathematics to basically do the same thing all over again. Right? And this will be, we already did most of the work here. So instead of a for loop, guys, instead of a for loop, I'll take this equation here again. And basically what I'm going to do is I'm just going to take that line of code. And now I'm just going to do vector mathematics. What's the vector mathematics that I'm going to do? It's actually going to be real easy. Look how much easier this is going to be. Oops, stop. Look how much easier this is going to be. R is simply going to equal this vector, the vector A, right? And so when I place a vector, right, when I do this math, P is a value, R is a value, P is a single value container, but R is a vector. So P will end up being 11,000, so there's no complexity here. But the complexity here is that this is a vector, right? So because this is going to be a vector, what happens is that all these numbers. It's the same way like we did a before when we did a equals a plus 5. Remember previously in our slides? Same concept, except it's just happening on a larger scale with more numbers. The first value of r, what r will do is it'll take, since this is 11,000, it'll take all these numbers and it'll place the first value of r in each one of these positions. Crunch numbers and put the value in result in RES. It'll take the second value of r, crunch numbers, put in RES. Third value in r, fourth value in r, fifth value in r, etc., etc., etc. A vector plus a number gives you a vector. A vector times a number gives you a vector. A vector divided by a number gives you a vector. A vector subtract by a number gives you a vector. Vector mathematics. So when I run this, notice there's no brackets here, guys. There's no need, because this will go ahead and generate the vector for us. See that? Vector mathematics in effect. And this works because, again, the properties of vector mathematics. R became a vector in line 153. R became a vector. And when R became a vector, right, everything we did with R became vectorized as well. How much easier was this and straightforward was this versus this? You see that? Much easier. And again, we would do the same thing here again. We would simply eyeball 65,000, lines 7 and 8. And then we basically could do the same thing again and say, hey, what's a 7 of 8? What's a 7 of 8? Boom, around 16, 17. But it's basically the same thing, except that a much reduced amount of typing is much more straightforward. Much more straightforward what happened there. All right, so that's the semi-barbaric way. And now we finally get to the right way. And this is what we'll use our optimizer called junior root. Okay, now I'm going to jump back into the slide. All right, so to use the uniroot way, we must understand what uniroot is doing. Uniroot is an optimizer that optimizes any kind of equation to 0. That's what uniroot does. It optimizes any equation to 0. So for example, if I wanted to, hypothetically, if I wanted to solve the equation 5x equals 10 for x, what x will give me, what x multiplied by 5 will give me 10, right? We know the answer, it's 2, right? Now, but let's say I wanted to rearrange this equation and solve it for 0 while solving for x. How would I do it? I would simply just say 5x minus 10 equals 0, right? 5x minus 10 equals 0. And now what I will do is, again, I'm doing basically the same thing. I'm solving for x such that the equation equals 0. It does not matter how complicated the equation is. It could be something like 5x minus 10 plus 8 minus 7, blah, 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 whatever. And throw another x in there, plus 3x equals 0. It doesn't matter. We would still do our algebra, and we would find the x and solve it so that this equation right here became 0, right? And in doing so, you would basically, what we do is we obviously would take all the non-constant numbers, move them to this side, so add 5x plus 3x, get 8x, etc., and solve for x, right? That is basically what uniroot does, except uniroot, let me comment this out. Except what uniroot does is uniroot requires a function that is written so that it must become 0. So taking this example right here, 5 equals 10, to solve this in uniroot, I would have to first write a function so that so that 5 times x minus 10 could become 0, right? And then what happens is, so I write this function right here, 5 times x minus 10. Notice I have the return there. I need the return. I need that output. And now, once I have that user-defined function, what I do is I pass that function to uniroot. Uniroot is a built-in function in R that optimizes any function you give it to be 0. Okay? Any function, notice uniroot takes 3 parameters: your user-defined function, a lower bound, and an upper bound. The user-defined function, uniroot, will attempt to solve this for 0, right? When I say it attempts to solve it for 0, what I'm saying is that it's going to keep throwing in parameters here into this function such that the output will become 0, okay? The parameters it'll be throwing in here for x, trying out all these different parameters, will start at the lower value, which is 0.05 in this case, and it'll go up incrementally all the way up to the upper bound, which is 10. It will only try the values within those ranges inclusively. All right, so that is how uniroot works. So basically, if I could show you, let me just copy this real quick. All right, so here, exmp is a function, right? And so when I do uniroot exmp, what was it, lower equals 0, upper equals what, 50%, whatever, right? Basically what it's doing is it starts with 0. Obviously there's a much more elegant mathematical way behind the scenes is doing this, maybe gradient descent or stochastic gradient descent, some sort of linear optimizer of some sort, right? We can always look that up if you want to see the details of uniroot. If you want to see the details of any function, by the way, this is actually a great point to bring this up. If you simply type in question mark and then the function name, right? Down here in the help tab, which is the fourth tab here in the bottom right window, it gives you a brief definition of how it works. The usage, the arguments, how fancy it can get, right? A full detailed breakdown of it. Let's see. Based on that. 0 n. So looks like it's using something from a different function. So for me to figure out which kind of algorithms is being used in the behind the scenes, I'd have to check out what 0 n is doing. The algorithm behind 0 n. All right. My assumption is it's some sort of stochastic gradient or gradient descent model or some sort of bisection method being used to some degree. These are some mathematical numerical techniques. Any math majors or minors here would know what I'm talking about, right? But we don't have to be. The beauty is we are R programmers. We don't have to know these methodologies. We could simply just use the function. All right, so here, what's basically happening here? When you do this, again, the 3 parameters, it's basically doing, okay, xemp, I'm gonna start with 0. Okay, are you 0? Let me scroll up. Right, uniroot's like, okay, start with the lower bound. Are you 0? You are not. All right, let me try a different number. Let me try a number. Now, obviously, it increments by some mathematical formula. I'm just gonna go by 1. So it's like, all right, cool. Try 1. You aren't 0 either, but we're going in the right direction. So let me continue going in that right direction. 2. Aha! You are 0. And then uniroot will give you the answer 2 back. Right? Uniroot will basically give you the answer 2 back. And that's basically, in a nutshell, how uniroot works. right? It all starts with the user-defined function. You must write your user-defined function, so when you're solving the function, you allow Uniroot the opportunity to solve for your parameter such that the equation within the function will become 0, right? And when I run this, uh, I get, oh, sorry, I did 0.5, I need to do like 5 or something here. Yeah, so this error basically right here, guys, some of you guys will see this error when you're doing a lab. This basically means that Uniroot could not find a reasonable answer because the range you gave it, the lower and upper bound range you gave it, was not large enough. You need a larger range. You need a larger range. So that's why we got that error, right? So I had from 0 to 0.5 where I should have had like 0 to 5. So I run this, and this is the result I get. I get 6 values back. Let's look at this. I get 6 values back in a very weird kind of output, and I'll break that down for you. Later on in the slide, I'll break that down for you, what's happening here. The result, actually, Uniroot gives us the result back as a list. List is a very special data container, not to be confused with lists in Python. They mean two complete different things. So list in R is a very special data container that is a data container of data containers. Okay? A list is a data container that can store other data containers. A list can hold other tables, simple values, other vectors, what have you. Right? It's a special thing in R that allows the functionality for programmers to store a massive amount of data containers in one data container. So in this case, Uniroot gives us back a data container with 6 values or 6 objects. All of this happen to be values. This dollar thing you see, dollar $f.root, $.iterate, anytime you see dollar something like this, that is just the name of the data container. So each one of these data containers have a name: root, f.root, itr for iteration, init.it, estimate.precision. So let's start off with what each one of these things mean. Root is basically the answer. Root is basically the answer. 2, root basically means what is the root value that makes the whole equation 0, right? So f.root basically is the final value of the function given this root value put in. And this basically tells you we got a perfect answer. The answer was 0, we got a perfect answer. This tells you how many times how many iterations Uniroot ran. In this case, it just ran 1 iteration because the answer, it was a very simple function for it to solve. It just needed 1 shot at it. This right here, I have no idea. I have no idea what this is, right? I would have to look it up to see what that is. And this right here is from computer engineering. The question is basically how much precision was given to the problem to solve it. When we mean by precision, meaning basically how much memory was allocated to the decimal places. That's basically what it comes down to. This is a computer engineering thing. How much memory was allocated to decimal places? How many decimal places were being used to calculate this answer, right? Here it's 3. It's not that many because again, it was a very simple problem, right? So this is basically the results you get back, and this is what your results basically mean. And the output is funky because it's in in a list, which again I'll talk about a little later on in the slide. All right, so that is how Uniroot works, right? Uniroot is based on the user-defined function, which must be solved for 0. How is this going to help us in our problem now? Right? How is this going to help us in our problem? And here, by the way, in this example right here, I stored it in a variable res, and that res became the list object. All right. So now let's talk about lists real quick before we come to the final conclusion of the solution of the elegant way to do it. So the data container res is a list right here. If I were to say res uniroot using this current example, right? Example lower 0.05, upper 10. So I just have a greater range right here. Right, I have a greater range. So a list, like I said before, is basically a data container that holds other data containers. To create a list, you simply use the list keyword right here, guys. To create a list, you simply use a list keyword. And here I'm creating a list called named, that will be L1. And within it, I have 3 different data containers. A, so I named this A, B, and C. Now, the data containers within L1 are very simple. They're just simply 3 vectors or 2 vectors in a single vector data container, right? So A is 5, 4, 3, 2, 1, B is 1, 3, 5, and C is 5, okay? And now if I want to get the specific data container within a list, you can do it two different ways. So let's say, so here I do res equals 1, right? So I can use the bracket system, or I can use $root, right? I can use the bracket system, or I can use $root. I mean, I can use the name system. So let me just copy and paste and show you what I'm talking about. So here, all right, go ahead, I run this. Right, so now you notice you have on the top right window, it's literally telling you have a list. And you can click on this and you can see the inner elements of the list, right? Very nifty. All right, so if I want to see a particular element, if I do L1 $, notice a drop-down list. See that dollar I do? You're going to see this a lot. That dollar basically means show me the elements within this data container. Or if it's a table, show me the column names of this particular table. In this case, it's a list. So you're basically saying, hey, show me the other data containers within this list data container. And obviously we have A, B, and C. So you can basically choose which one you want to see. And it gives you the results. Also, what you could have done is you could use, just like we have the bracket system to look through shelves, we have the bracket systems for lists, 2 brackets. So if I did LL1, bracket 1, it's going to give me the first data container, and L1, bracket 2, would give me the third data container, and so on, and so on, and so on, right? And so on, so on, so on. The reason why they give a double bracket system is because it allows us to actually drill down even further into the data container. So let's say, for example, I want to see the second element of the second data container. So after that, I would place my single brackets. So the 2 double brackets first chooses the data container within the list, the single brackets, and chooses the element of that data container. And that's how I get the value 3. And vice versa. You can also, not only am I calling them, but I can also, right, I can also change those values. So if I wanted to change let's say I want to change the 4 in the first data container to 40, then I would simply do L1, bracket 1, bracket 2, and make that equal to 40. Right? And if you type in L1 $A, you will see the second element is now 40. You will see the second element is now 40. Okay? So these are basically lists, and a lot of third-party packages, they tend to, when you're running their functions, they tend to give you the results back as lists because they have a lot of data coming back at you. So in this particular example, Uniroot has 6 things that basically, 6 type of result it gives back to you when you use it, and it labels them clearly, and it uses lists to do it. It uses lists to do it. All right. So now we are ready to tackle our final solution. All right, solution. So here's the solution. I will work this for you. Let's start with our semi-barbaric way and go from there. All right. So here, this is our semi-barbaric way, right? Now, as we know, we need a function, right? We need a function. So I'll call this function lab1. And within the function, remember, we want Uniroot to keep changing the compound rate. So if we want Uniroot to keep changing the compound rate, then that is what will go there in the parameter of a function. Boom, done. Now, we need an output because Uniroot needs to see the results. So here I have res. Let me change this to t. And we're going to output the results of t. Excellent. So far, so good. Now, all right, and let me put my P in there just so the function is complete. Now, there is one thing missing here, ladies and gentlemen, for us before we can use this function. There is one thing missing here, right? Remember, we want Uniroot to solve for r such that this equation is 0. Will this equation be 0? No. We want r to solve this equation so that this part becomes 65,000. But in order to do that, this function needs to be solved for 0. How do we solve it for 0 then? You simply subtract from the value that you want this whole thing to be, right? So we want to find the r that will make this 65,000. In order for Uniroot to be able to do that, we need this whole function to become 0 when the correct r is found. So how do we do it? We simply subtract what we want that part of the equation to be, 65,000. And now, just like before, when we took the 2x equals 5 and we brought the 5 over it, the 2x minus 5 equals 0, Uniroot can now solve this function for an r so that the function gives an output 0. And when the function gives an output 0, then Uniroot has found an r so that this first part is equivalent to this, which is 65,000. That is the trick here, guys. That is the trick. So I process this. You notice down here in your functions, lab 1 will be there. Let me scroll over so you can see it. Lab 1 is written. And now I'm ready to use Uniroot. RES. Now we already know what the answers will be, but because we sort of saw it in a different ways, but nevertheless, my lower bound I'll start with 0. My upper bound I'll go to 50%. I run this. I have RES, where I have my results. I can do RES $root. Remember, that was my answer. And the answer comes out to 16.23%, basically. So my fictional students generated a compound return year over year on their education, their investment, if you will, their tuition, their tuition was an investment. That tuition generated in these 4 years a year over year compound return of 16.23%. Not bad, not bad at all. And who says college doesn't pay? All right? So now you can go back to your parents and your friends and say, hey, let me tell you how much my education generated. Compound return. What kind of compound return my education generated. And again, this is the equivalent of you taking your 11,000 every year and putting it in a bank account that gave you an interest rate of 16.23%. 16.23%, which is obviously there's no such thing as a bank account that gives you 16.23%. I think they're all virtually almost 0 at this point. All right, year over year. So cool. So look, guys, at this point, we're done. We're finally done with lab 1, right? And obviously, we took the long way around because I wanted to basically use this as an opportunity to break in, introduce R to you. So this is your first step in doing R. And so what I want you guys to do is, firstly, I want you guys to run my example. Make sure it works, right? So make sure your code is correct, everything works. And then what I want you to do is I want you to calculate your personal compound return. And again, you guys already know what your P's are. And yes, in your function, some of you guys will already ask me the question, hey, my tuition rates were different every year. So just put them in individually, whatever they were, your freshman year, your junior year, your sophomore year. Remember, your freshman year obviously has the largest exponent because that money will be invested for the longest amount of time. And your senior year will have just an exponent of 1 because it's just going to be invested for 1 year. So you can customize those P's year over year. I mean, for every year. That's number 1. Number 2, estimate what you think you'll make. Right? You guys have a great idea about what the salaries are from your friends. All right, from the market. Like I said before, 65,000 I got because that's usually what the consultant companies package-wise they tend to give our BATE students. All right, and I mean that could be higher, that could be lower. Obviously, it's all over the place. So Stick that number in there. And you have to use a little bit of common sense. Remember that the P's, in our example, P is 11,000. So I have 4 P's over here, right, that, will be 44,000. The 4 P's altogether. So you're invested total 44,000 over these 4 years. That 44,000 is obviously less than 65,000, which implies that our compound return is positive, right? Because you have to go from 44,000 to 65,000. So our compound return is obviously positive. Some of you might have a situation where your tuition, the total amount of your tuition, will be greater than your first year compensation, right? That's going to imply a negative compound return. Don't freak out in that situation. Just make sure your lower bound and your upper bounds are wider to encompass the negative numbers, right? Or more accurately, what you might probably want to do is instead of using your single year salary, you might want to use your double or triple year salary. All right, so basically you want to take either instead of your single year, you might want to take your salary for the first 2 years of your working or the first 3 years of your working, right? But basically, come to a number so that this number right here would be greater than the total amount that you invested in your education. If you have a negative compound return, don't freak out. Remember that your salary, uh, you're going to get that salary is your starting point salary, and you'll be getting that every year. You'll be getting that every year, if not, more growing. All right. So when you factor all those things in, you guys will come to your own compound return. And so basically, after you do the lab, I'll ask you guys on the for the lecture, hey, what compound return did you guys get, right? And you guys can, once you finally get to this point and do it, you guys can tell me, either privately or publicly. It's totally up to you guys. All right. So this concludes our part C of Lab 1, and we're finally done with Lab 1. The next video will be our practice set video. All right, thank you guys. I'll see you guys on the next video. All right, bye-bye.